Can you now? Yeah.
Yes.
Okay. Yes, it is recording. So we can start. Yeah.
Yes.
Okay.
Okay.
Right.
The next speaker is Sarthak Parikh, and he will speak about non-Archimedean holography beyond Bruhat-Tits. Please.
Yeah, thank you. Let me start by thanking the organizers for putting together a nice conference in these challenging times, and also for giving me an opportunity to speak. I'm the last speaker for this session, I guess. And one of the advantages of being the final speaker is that a lot of the previous speakers have already introduced and explained, sometimes multiple times, many of the ingredients which will go into my talk. So for example, you've seen ADS-CFT been discussed multiple times. Ingmar Saberi mentioned it, Ling Yanhung mentioned it, Abdel Malik Abdusalam mentioned it, Hao Yusun also mentioned it in the previous talk. So that's what I mean by holography here, ADS-CFT. And Bruhat-Tits tree has also been introduced multiple times already. I think first were in the context of tensor networks, then hierarchical models and p-Adic string theory, black holes. So, and obviously the audience is familiar here with p-Adic numbers and non-Archimedean norms. So hopefully all the words in the title should be familiar to most people. But in any case, let me say a few words about what I will be talking about today. So my talk is split into two sections. So in the first part, I will present some results on extending holography done on Bruhat-Tits tree to real holography. So trying to go from the Bruhat-Tits to Archimedean holography, how to extend, how to recover Archimedean holography, or at least parts of it. And we'll do that to obtain some new results, which were not previously known. My philosophy about going from p-Adics to reals or reals to p-Adics is I'm agnostic about whether the underlying p-Adic techniques are physical, they have some physical meaning, or they're just a mathematical auxiliary tool which helps us solve some hard problems over reals. So I mean, it would be nice, like Professor Wolovich has been conjecturing for a long time, that maybe there's something, could be something physical behind the p-Adic techniques, but here I will just mostly be using them as a mathematical tool. In the second part of my talk, which will be shorter, I will mention some other directions. These will be different from the first part. So here I will talk about extending the p-Adic results over Bruhat-Tits tree to larger p-Adic spaces and arguably more interesting p-Adic spaces. So kind of like going beyond Bruhat-Tits tree in the setting of non-Archimedean holography itself. Okay, so previous speakers have actually, I think I've included a kind of like a summary of some of the things previous speakers have talked about, which I could have potentially included in my talk today because they do fit the overall theme. But fortunately, the things I decided to talk about today do not have a substantial overlap with the things listed here. But if you're interested in any of these things, I encourage you to look at the talks by these respective speakers. And okay, so before I begin my talk, I wanted to take a moment to remember Steve Gupser and share a small story about him as well. So Steve was a well-known and brilliant physicist and a great human. And he spent about his final 3 or 4 years working on p-Adic physics very enthusiastically. And he was one of the strong proponents of doing p-Adic stuff in the past few years. We got started on p-Adic mathematical physics and p-Adic ADS-CFT with our paper, which we wrote in 2016. And this paper came about due to some serendipitous encounter. So it wasn't something which we were planning to do. So we were attending an advanced number theory class for unrelated reasons at Princeton. taught by Peter Sarthak. And in one of the classes, Peter Sarthak mentioned Hensel's lemma, and this piqued Steve's interest quite a bit. And he started reading about it, and obviously about p-Adic numbers, which comes with Hensel's lemma. And this led him down some literature hunt and some older literature from many of the people who are in the audience. And basically, he realized immediately that p-Adic numbers are tailor-made for ADS-CFT. And this is when we got interested, and none of us knew anything about p-Adic numbers at that point. So we sat down, learned about it, and wrote this paper. And since then, Steve actually worked on p-Adic physics almost exclusively. He published about maybe a dozen more papers until his tragic climbing accident. But yeah, he's sorely missed by the community. I just wanted to say a few words about him as a tribute. And now I'll proceed with my talk. Okay, so the first part of the talk is, as I said, new Archimedean results obtained from non-Archimedean holography. So let me still quickly review Archimedean holography very qualitatively. We've seen introductions to ADS-CFT multiple times already in this conference, but I'm going to present it maybe more pictorially and qualitatively. So Archimedean holography is basically some kind of an equality between a theory of gravity in d+1 dimensions in some asymptotically anti-de Sitter spacetime, and a conformal field theory, which is living on the boundary of that spacetime. So this is what we call the ADS-CFT correspondence because of the ADS and conformal field theory. And the picture I usually have in my mind is that of a cylinder. So this cylinder represents ADS space, and the gravitational theory is inside the cylinder, and the conformal field theory lives on the boundary of this cylinder. So the metric obviously on the cylinder is different from the usual cylinder metric. This is the ADS negatively curved metric. So I've just given it in global coordinates here in case you're not familiar with this, but this is not very important. One important thing about ADS-CFT correspondence, and I think this has been mentioned also multiple times already, is the fact that it's a strong weak duality, by which we mean that if the gravitational theory is weakly coupled effective field theories, and we can do perturbation theory here, then the dual conformal field theory is in some strong coupling regime where we do not have access to perturbative methods, and vice versa. So that's the regime we are going to be interested in. I'm going to be interested in the regime where the gravitational theory is some weakly coupled effective field theory, where I can do some kind of perturbative Feynman diagram analysis in order to help compute observables in the strongly coupled CFT, where I do not have access to compute correlation functions directly in the boundary theory. So I have this equal to sign in quotes in all these slides so far, and that's because I haven't really told you what I mean by equal. And in the previous few talks, you've heard people say that there are many dictionary elements. So the dictionary tells you precisely how the theories are equal to each other, in what sense they are equal. And there are many elements. I don't want to spend time on that. People have described various kinematic or symmetry-based elements of the dictionary, and also dynamical theory-based elements of the dictionary. I just want to focus on a special case. So one of the dictionary elements is that the generating function of correlation functions or moments in this conformal field theory is equal to the path with the gravitational path integral with appropriate boundary conditions. And I have in mind a weakly coupled gravitational theory where we can do a perturbative gravitational path integral and use that to compute observables. If I'm available. Can people hear me?
Yes.
Okay,
Yes,
great.
Yes, it's okay now.
Okay, okay, thanks. So conformal field theory is a special kind of quantum field theory where the invariant under a larger symmetry group than Lorentz invariance. So conformal group, you can also call angle preserving transformations. And I just wanted to say that in conformal field theory, the important point is that we have access to operator product expansion, which means that we can decompose any higher point correlation function into a combination of 2- and 3-point correlation functions by repeated use of OPEs. And what that really means is that the full data of a conformal field theory is stored in its 2- and 3-point functions, which essentially corresponds to the spectrum of the CFT and its OPE coefficients. So just some basic facts. You will see OPE coefficients appear later, so I just wanted to mention that. Okay, so let me go to a specific element of the dictionary. So this is obtained from the path integral element of the dictionary, specialized to the 4-point function. So the dictionary says that the 4-point correlation function in a conformal field theory is equal to a Feynman diagrammatic expansion in the gravitational theory in ADS space. So we have what I have shown here in 3-dimensional sketch is basically how we would write like a 4-point function in quantum field theory, except for the fact that I've shown a disk which represents that this interaction is happening inside ADS space. And this blob represents all kinds of possible interactions which are allowed by the gravitational theory. So if the gravitational theory, for instance, has a quartic interaction vertex, then this kind of a Feynman diagram is possible. If there are cubic vertices, then these kinds of diagrams are possible, plus ... So there will be a perturbative expansion and there will be some coupling constant. So you can expand perturbatively and try to compute the CFT correlation function using Feynman diagrams in ADS space. Excuse me. Okay, so here I've told you about one dictionary element, which is 4-point function written in terms of perturbative Feynman diagrammatics. Likewise, you can have a 5-point correlation function in CFT, which will have a perturbative dynamics with 5 external legs. And there will also be at higher order loop diagrams, etc. Okay, so conformal blocks are going to be important for the first part of the story. So let me introduce them now. So conformal blocks are theory-independent building blocks in conformal field theories, which are fixed entirely by conformal symmetry in principle. And they are important because they give a basis for correlation functions in CFTs, and in fact, a very convenient basis. So we can decompose a conformal correlation function with the help of conformal blocks into theory-dependent and theory-independent pieces. So theory-independent pieces would be like contribution coming from multiplets, and theory-dependent pieces would correspond to which multiplets are going to be present in the correlation function and what are the OPE coefficients. So conformal blocks are actually extremely basic objects in CFTs. And there is a way of defining them rigorously. There are many ways. I guess one quick way of saying what conformal blocks are is they are eigenfunctions of the conformal Casimir operators of the conformal group with satisfying particular boundary conditions. So they are important objects and they're very useful in CFTs. So one question which is very useful to answer is, what is their explicit form? Can we write them down explicitly, or is it just that they're guaranteed to be, they're completely determined from symmetry, but is that just in principle or is that true in practice? Can we write them down? So that's the first question. And the second question is, since conformal blocks are very important in CFTs and we have the ADS CFT dictionary, what is their ADS interpretation? What is the holographic dual of conformal blocks? Because those objects should be important in the gravitational theory. So it turns out that these two questions did not have a satisfactory answer outside 4-point correlation functions and 4-point conformal blocks. So 5 point onwards, they did not have an answer. And that's one of the things which we will do in this talk today. I will review very briefly what we did and how we used p-Adic holography to solve this problem over, I mean, this is a big problem over real holography, unsolved problem over real holography for the past, 2 decades or so. So we will see how to leverage p-Adic methods. So the point will be to solve those problems. The strategy is can we find a simplified toy model of holography where we can solve these problems and then get inspiration from this toy model to tackle a harder problem over, the full real ADS CFT. So from here on in this talk, instead of viewing ADS space as a cylinder, I'm going to go to a hyperbolic disk. So there's 2 ways of thinking about it. You could think of the hyperbolic disk as just some time slice of ADS space, or you could think of the Euclidean version of ADS space is like a hyperbolic ball. But in either case, from now on, I will be looking at disks. So for simplicity, you can just think of this as some time slice of ADS over which I'm interested. So one of the possibilities for a toy model, and this was discussed in the context of tensor networks previously, is can we consider tessellations of hyperbolic space, some kind of discretization, because a lot of times discretizations makes things easier, at least some things easier, like calculations can become easy. So yeah, maybe, we want to tessellate hyperbolic space. This is what tensor network people do, right? They tessellate hyperbolic space and they put a tensor network on this discretized space. So maybe to answer our questions, we need to do that. Is there a question? Maybe not. Okay, so we can tessellate the hyperbolic space. This is a very familiar tessellation, 5,4 tessellation, because 4 pentagons meet at every green vertex. So 4 pentagons meet at every vertex. That's one possibility of discretization. We can also try some variants. For instance, I could tessellate with octagons. So now 4 octagons meet at each green vertex. So it's called 8,4 tessellation. And you can imagine bumping up the number of sides of the polygon to higher and higher numbers. There will always exist a tessellation. So you can turn 8 into 1,000, 2,000, up to infinity. When you go to infinity, I'm sure you can already imagine what you get is the basically the topologically the graph theory equivalent of Bruhat-Tits tree. So now there are no loops anymore. This is a regular tree of valence 4.4 because 4 edges are incident at each vertex, and it goes on to infinity. I have only shown a small part of it. So a tessellation, this is an extreme tessellation of hyperbolic space, which leads to the Bruhat-Tits tree. So you've seen different ways of thinking of Bruhat-Tits tree. I just thought maybe I'll show another naive way of thinking of Bruhat-Tits tree, and we'll come back to some more mathematical properties of Bruhat-Tits tree in the second part of the talk. So the 4 here actually can be replaced by p+1, where p is any prime. Actually, you can be even more general and replace it with some powers of p+1. But for simplicity, let's just say p+1. And in these examples, p is 3. But you can choose any prime, and it will be good. So the first question which might come in our minds is, this is a very drastic discretization of the hyperbolic disk we started with. Does holography even survive after such a drastic discretization? And we all know now that the answer is yes, holography survives. This is what I'm calling p-Adic holographic correspondence, or like a vanilla version of p-Adic holographic correspondence. So the original holographic correspondence I've written here takes this form. So the gravitational theory in d+1 dimensional asymptotically ADS space becomes some kind of a statistical model on asymptotically tree-like graphs. So this is the simplest version of p-Adic holography. So you have some statistical spins on asymptotically tree-like graphs. That's plays a role of the gravitational theory. And then the conformal field theory is still a conformal field theory, except now it's the conformal field theory on the boundary of this tree-like graph, which turns out to be the projective line over some p-Adic field. So I've tried to show here the same figure, but maybe different color scheme. This is again for p equals 3 and goes to infinity. And the boundary is what is the p-Adic numbers, the projective line over p-Adic numbers. And the bulk space is what we call the tree-like graph, which is asymptotically. Here it is exactly tree-like, but more generally, there could be complicated structures in the middle, but asymptotically tree-like. And if that is the case, it's good enough. Okay, so let's look at these statistical models and conformal field theories quickly, what they kind of look like. So the statistical model on the tree, the simplest ones look like graph, statistical models on graphs. And so there's a kinetic energy term, which is, the discrete version of the, phi dot term, or like phi box phi term. And then there's a mass term, there's various polynomial interaction terms, and there could be any kind of term you can imagine. So there could be quartic, quintic couplings, there could be nearest neighbor couplings, next to the nearest neighbor couplings, next to nearest neighbor couplings, etc. So all of that is fair game. And whatever you choose here kind of defines your effective gravitational theory. So different choices of coupling constants and couplings will, correspond to different kinds of CFTs on the boundary. So the simplest thing I will be focusing on today is that the fields phi are defined on the vertices, not on the edges. So we just have the vertices where they have some scalar field which is fluctuating. There is no gravitational degree of freedom. So it's like some kind of statistical model on a fixed background. The conformal field theory on the boundary has been, again, studied for a very long time by many people in the audience, and also recently by us from the point of view of ADS-CFT. And the idea is that the conformal field theory on the boundary is a non-local field theory. So you can write down some kind of you don't always know the Lagrangian. Whenever you can write down a Lagrangian, it will be some non-local Lagrangian. It's non-local because the kinetic energy term is given in terms of the Vladimirov derivative, which is a pseudo-differential operator. And then you can have additional terms. So here I've tried to show some kind of a ON model, 5/4 ON model, where the I index can run from 1 through capital N or something. And I've just for fun, I decided to specify the integration region to be V, and then say V can be either p-Adic or real. And that's because actually it turns out that you can describe both real and p-Adic theories at the same time. And this is not something I will be spending time on, but I wanted to say that, for instance, when you set S equals 2 and V is over reals, then it turns out that this gamma function, which is some kind of a Gelfand-Greif gamma function, actually has a pole at S equals 2. And that pole turns this non-local interaction, non-local kinetic term into a local usual kinetic term for quantum field theories over R. So this describes, in some sense, both real and p-Adic theories at the same time. And then you can, in one of the papers, this paper, we actually computed anomalous dimensions, both for both real and p-Adic theories, and we wrote down one unified formula, which kind of, you tell me whether the field V is p-Adic or real, and once you input that formula spits out the anomalous dimension accordingly. So it's one unified expression, which is kind of nice and interesting. Okay, so what do we gain or lose when we do this extreme discretization? It seems like we have some p-Adic ADS-CFT correspondence, but what are we missing out on, or what are we gaining? So the first thing to notice is that this was mentioned already in the context of tensor networks, that once we start tessellating, we are kind of losing a lot of symmetry, which was originally present. And that makes things usually harder. But it's interesting that when you do an extreme discretization and you get to the Bruhat-Tits tree, then the symmetry is in some sense restored. So conformal symmetry group is restored in the sense that, excuse me, the conformal symmetry group becomes the PGL2 group over the p-Adic field as opposed to the SL2R. So we get some, general linear group over some other field, but at least it's like it looks like a nice conformal group with, it has linear fractional transformations and all the nice global conformal group properties. The discretization is also useful because it gives us a simple framework. So the bulk is simple because we have a discrete tree-like model. The boundaries also actually turns out simple because doing p-Adic integrals, people who have done p-Adic integrals in the audience know are, generally easier. You can break them down and write them down explicitly. So the bulk and boundary theories are both easy, and roughly the theme is that integrals become geometric sums. So, there's a higher hope of being able to compute something directly, even by brute force. So this is just a snapshot of some of the things we gain. And some of the salient things we lose out on are that, as I mentioned already, the CFT becomes non-local over p-Adics. So over p-Adics, there is no value of S you can choose in the previous slide that the kinetic term becomes local. That only happens at integral values of S for real CFTs. But for p-Adic CFTs, they remain non-local, which means that there are no conserved currents, no local conserved currents. So, for instance, there is no simple way of getting a stress tensor in these simple models. You have to do something more. So I should say, maybe if I wasn't clear, all this time, in this entire talk, I will be talking about conformal field theories and theories on the tree, which are real valued fields or operators. So I will not be talking about the space, the background space is p-Adics for the CFT, but the operators are from p-Adics to R or C. So that's why we have no local conserved currents. And also another thing, a point to mention is that the signature, it's much more convenient to think in terms of Euclidean signature over p-Adic CFTs than Lorentzian signature. That can be slightly tricky. So we will have Euclidean signature. So this is kind of like Wilson's talk was, statistical field theory, because quantum field theory with Euclidean signature is like statistical model. Okay, so now let me explain why, well, not really explain, but just quickly demonstrate one element of the dictionary. I showed you an element of the dictionary, which was the 4-point function. Here's the 3-point function, and this is the Mercedes-Benz diagram, which Malik talked about. So at leading order, the 3-point correlation function in the CFT will be given by this cubic interaction vertex, where the green point is integrated over all of ADS space. And then there could be higher order corrections, including loop corrections, etc. But to leading order, this is the Feynman diagram you have to evaluate. So this is the diagram we can evaluate. And I've shown the full calculation here. I won't go over it, but it's simple enough to write down on 40% of the slide. And you get the final result, which has some overall factor, which turns out to be the leading order contribution to the corresponding OPE coefficient for this theory, and the expected scaling of the 3-point function. So one nice thing is that, well, the corresponding result over reals was known for 20 years. And that result takes the following form. So now I'm going to show you an adelic formula. So this is from the previous slide, where zeta sub p is the same local zeta function, which was used in many talks previously. And this is the p-Adic norm, and delta is the conformal dimension of the conformal, well, primary operators here. And I've chosen D here because I'm kind of thinking in terms of a D-dimensional, say, unramified extension of p-Adic numbers, but you can also just set D equals 1 to deal with p-Adic numbers. Over the reals, this result has been known for a long time, and it's a very easy calculation, actually. The corresponding formula takes this form. So infinity is just to represent the reals, and zeta infinities are functions which are defined here in terms of combinations of pi's and Euler gamma function. And then you have the L2 norm of the distance between the insertion points of these operators. So you can see that these formulas look almost identical, except that P can be replaced by infinity. And that's not a coincidence. I mean, there's something deeper here, because you can take an adelic product over all the p-Adic 3-point functions, all primes P, times the Archimedean 3-point function, and the position dependence cancels out, and we get a compact expression in terms of a well-known object. So this is the completed zeta function, or like the simplest version of an L function. And this completed zeta function is given by this Archimedean factor, the factor at infinity, times the product over all these local zeta functions, which Euler product formula we know gives the Riemann zeta function. And so this completed zeta function satisfies nice functional equations like L functions are supposed to. So here's this nice product formula I just wanted to show explicitly. And versions of this were already known in p-Adic string theory literature, where it was a much simpler result for, say, the 4-point Veneziano amplitude, where the product was just 1, but there were like extensions where you had some number theoretic factors appearing on the right hand side. And just because I had some space at the bottom, I also decided to show the result when all the operators O's are actually distinct. So I'm calling them O1, O2, and O3 with conformal dimensions delta 1, delta 2, delta 3. Then, I mean, this is some combination, linear combination of deltas, which I will define later, but it's not important. But, again, it takes a very convenient and nice compact form, the product formula. And since in CFT is basically 3-point functions and 2-point functions are everything, in some sense, this 3-point adelic formula is, the very important object, very important result, because it guarantees that there will be interesting properties at higher points. So just to summarize, the key takeaway is that in ADS CFT over p-Adics and Archimedean case, kind of like very similar to string theory over p-Adics and Archimedean case, there are these product formulas which exist. And also, please feel free to unmute yourself and ask questions if you have any at any point. So, okay, so now let's come to something new. So far, I have not said anything new about Archimedean holography. I said that we already knew the 3-point function in Archimedean holography, and we just saw that there was a nice adelic formula. But can we actually derive something new which was not known, maybe because it was too technically complicated, or there was some other reason? So can we find some new results? And the answer is yes, actually we can. And let me try to explain that with the help of the next 2 slides. So what I have shown here is a Feynman propagator identity on the Bruhat-Tits tree. So this is an identity between a product of 3 propagators. For the cognizant, you might recognize these as the bulk-to-bulk propagators. And they are labeled by some conformal dimensions. But from the Feynman diagrams in QFT point of view, you think of these as 3 Feynman propagators with some masses meeting at some green vertex, and this green vertex is to be integrated over all of space. In this case, Bruhat-Tits tree, right, which is the discretization of ADS. So such propagator identities actually turn out to be very useful when trying to evaluate higher point Feynman diagrams in ADS space, also called Witten diagrams. But it's interesting to note that such basic identities, which are actually very basic if you think from the point of view of flat space quantum field theory, were not known in ADS space. So propagator identities are usually very hard to compute in ADS space because of the curvature of ADS space. So even something as basic as this wasn't known. And what we did was we first worked it out on the Bruhat-Tits tree by explicit brute force calculation. It was a very simple calculation you can probably do in 1 hour or less than an hour. So when you do that calculation, you find 4 terms. So 1, 2, 3, and 4, and some coefficients multiplying these terms. And these terms on the right-hand side do not contain any bulk integration. So these are now expressions without any integrals. And these lines represent that now there is in some sense, this is a version of a star triangle identity in flat space QFT, that a star combination of propagators integrated over the meeting point gets replaced by a triangle combination and almost triangle combinations. And the point is that this line represents the unique geodesic on the Bruhat-Tits tree connecting the bulk point WC with WA and WC with WB and WA with WB. So I've just shown them as a triangle, but we obviously know that on the Bruhat-Tits tree, there are no loops. So this is triangle just schematically on the Bruhat-Tits tree, they will all meet as a star combination. But over reals, it turns out that, you can have propagators like this. But the point is that there are these coefficients here, which are actually precisely the OPE coefficients I worked out on the previous slide, the 3-point OPE coefficients. Yeah, these ones, or these ones, or the more general ones at the bottom of the screen. So these are the same OPE coefficients which appear, and there are some other coefficients which appear. Now, the point is that I think some people have already mentioned this in their talks, that the p-Adic CFT and real CFT are related to each other by the fact that the p-Adic CFT captures the primary contributions of real CFT. So that means that since there are no descendants in p-Adic CFTs, they are only able to capture the primary part. And in fact, that is true even in this propagator identity. So once we knew the Bruhat-Tits identity, we basically were able to immediately guess the identity on ADS space over reals. And if I go back and forth between these slides, you will see that the only difference is that I have changed the coefficients here, made them green, and put a hat. And by that, I just mean that these coefficients are related to the p-Adic coefficients by product formulas, essentially. And this combination of dimensions, here's what the linear combination is, stays exactly the same over the Bruhat-Tits tree or the ADS space. So that's kind of very powerful. The only other difference is that, as I said, the real CFT contains descendant contributions. So we have to add descendants. But once we know the primary contribution, working out the descendants turns out to not be that hard. So starting crucially from p-Adic identities, we were able to obtain the real identities. And I just wanted to point out that this is an extremely special case of a very famous identity in a very famous classic paper on ADS CFT from 20 years ago, which was very useful for many reasons. But here, this is a significant generalization of that. We'll be able to motivate from p-Adics. So let me just give you some results. I promised that I will tell you what the holographic duals of conformal blocks are. It turns out that this result for 4-point conformal blocks was known. So on the left-hand side, I have shown a Witten diagram where the green vertices are integrated over all of ADS space. And it turns out, starting from this and using a combination of the propagator identities like the one I showed in the previous slide, well, simple versions of that, because this was known in 2015, you can work out that the conformal block in ADS space is actually similar to the Feynman diagram, except for the fact that the blue vertices are integrated over boundary anchored geodesics rather than whole of ADS space. So basically, the bulk dual of conformal blocks are these geodesic diagrams where integrals are restricted to geodesics. but it was not known how to generalize this beyond 4 points, as I mentioned. And this is where the identity on the previous slide was useful. And we were able to generalize to many higher points. Let me just show one example of the 6 point. So here's a 6 point Witten diagram, 4 integration vertices in the bulk, 6 external legs. And you might notice this star combination in the middle. That star combination essentially turns into the triangle using our identity. So the geodesic diagram over 6 point conformal blocks is, takes this form. And it turns out this is exactly the same answer you get over p-Adics as well. The only difference between a p-Adic conformal block and a real conformal block from the point of view of holography is that the real conformal block has some descendant contributions, which kind of dress this term. But for the p-Adics, this is the exact contribution. So let me just quickly say what are the kind of results we found. So as I said, only 4 point was known up to 2015 and 5 point was known up to 2018. And it turns out after 5 point, there's actually many distinct and independent types of conformal blocks at higher points. So for instance, at 30 point correlation function, there are actually order of 10 million different conformal blocks you can use depending on how you take operator product expansions. So working each of these out one by one is hopeless. And this is basically where we used, again, the knowledge of primary contribution from p-Adic holography and the propagator identities and other such, inspiration to be able to work out all these cases in one go in terms of something like Feynman diagrams in, QFT. So all of these were worked out in one go. So I think it's important to, again, stress that this was possible essentially because of the crucial input from p-Adic holography. Okay, so now I'm coming to my final, second part, which will be short. So I think I will be able to finish in time. So the second thing I wanted to mention was the Bruhat-Tits tree and how to refine it or how to expand the Bruhat-Tits tree space. So let me start with the comparison of hyperbolic disk and Bruhat-Tits tree. And you should have seen this from previous talks as well. So the hyperbolic space and Bruhat-Tits tree are both homogeneous spaces. So this is hyperbolic disk, for instance, is the Riemann symmetric space by when you quotient the isometric group SL2R with the maximal compact subgroup SO2R. On the Bruhat-Tits tree, you quotient PGL2QP with PGL2ZP to get the Bruhat-Tits tree as a set. So this gives you all the nodes of the Bruhat-Tits tree. Another nice way to think of the spaces is as the space of norms on R2 up to scaling. And likewise, the Bruhat-Tits tree is given by a space of norms on QP squared, the vector space QP squared, not the squares in QP mod scaling. And as we've discussed already, the boundary of these spaces is the projective line over R or QP. And another interesting point to note is that the volume in these spaces actually increases exponentially like we expect them to. So in hyperbolic space, the volume of a ball of radius R increases exponentially with R, where L is the radius of curvature of that hyperbolic space or ADS space. And turns out something similar happens over the Bruhat-Tits tree, that the volume grows exponentially with R, where R now is the distance from some node. So R takes basically integral values, and L sub P turns out to be the equivalent of ADS radius, and it's actually proportional to 1 over log P. This was also something which I think like Zabrodin noted very early on in the late 80s. The 1 here comes from the fact that I set the edge lengths to 1. The important point to note is that here the distance between nodes is integral, which means that the nodes of the Bruhat-Tits tree are approximately 1 ADS length or more apart from each other. So, if you wanted to describe ADS physics in ADS space at length scales smaller than 1 ADS radius, the Bruhat-Tits tree is not a good space, because there is no, the nodes themselves are separated from each other by order ADS length. Over R, we know we can take R of any radius, capital R, to be as small as we want or as big as we want. So we have sub-ADS effects. So one of the drawbacks of Bruhat-Tits tree space is that how do we describe physics at small length scales, smaller than ADS length scales? Another drawback of this space is that actually the boundary is an uncountably infinite set, while the bulk is countably infinite. So there's some weird notion of the cardinality of boundary and bulk, which does not really match with what we expect over reals. So again, that points to the fact that this space is actually a very coarse-grained space, which can only capture long distance effects. And if we want to capture short distance effects, we have to actually add more points, which are missing from the Bruhat-Tits tree. So there are two ways I'm going to share with you of adding some extra space into the Bruhat-Tits tree to make it suitable for describing sub-ADS physics, which would be interesting to follow up on. So the first thing is what we call p-Adics in this paper. And it goes as follows. So let me do this by analogy. So the hyperbolic plane can be thought of as the open interval from 0 to infinity times the real line. And you can extend whatever I'm saying to higher dimensional hyperbolic spaces by just changing this factor here by a higher dimensional factor. Now I'm going to define a distance measure called u sub infinity, which is actually in the embedding space just the normal usual notion of distance, where eta mn is some Minkowskian diagonal metric in d+2 dimensional embedding space, and z and w are the coordinates, global coordinates on the hyperboloid, which defines the hyperbolic space. So this quantity in Poincare coordinates turns out to be this factor here, where z0 belongs to r plus and z belongs to r roughly. Same with w0 and wr. So this is the notion of distance, which I'm going to call caudal distance. Now let's try something similar with p-Adic spaces. So why don't we start with some space which we call p-Adics2, and it's defined as a product or direct product of the units in QP times the full QP. So it's supposed to be an equivalent, somehow equivalent to this hyperbolic product here. So this is a larger space than obviously the Bruhat-Tits tree, because there's more points here, and you can again extend it to higher dimensions by, for instance, changing the extension of this field to some higher extension field. Now, in analogy with this caudal distance here, we have defined another measure of distance. We replaced all the norms by p-Adic norms, and then whenever there's a plus sign, we replace this with a sup norm. This is kind of like what you do in vector spaces, high dimensional vector spaces. The norm is basically given by the sup norm. So we define something like this. And this is not ad hoc, because actually it turns out that the points of Bruhat-Tits tree are, so if z0, z belongs to qp star times qp, and z0 is of the form p to some integer, then this point belongs on the Bruhat-Tits tree. So I don't have time to explain why, but that's the case. So if z0z and w0w are both of this form, that w0 and z0 are integer powers of p, then this caudal distance actually becomes the graph distance. So p to power the graph distance between those nodes on the Bruhat-Tits tree. So this is actually a nice measure. It gives you a nice intuitive object on the tree, but it gives you, it gives you a way of describing other points in this larger space. So what exactly is the relation between this direct product space and the Bruhat-Tits tree? And it turns out that the answer is that the Bruhat-Tits tree is actually a coarse-grained version of this p-Adic space I mentioned. So what exactly do I mean by coarse-grained? I mean that if we define an equivalence relation of this form, that 2 points in this direct product space are equivalent if the caudal distance between them is less than or equal to 1, we identify all those points together. Because of the non-Archimedean property of the norm, they cluster into nodes, and each node corresponds to is in one-to-one correspondence with a node on the Bruhat-Tits tree. So again, I don't have time to prove this, but that's the coarse graining that from QP cross QP you can go to Bruhat-Tits tree by such equivalence classes. And it's actually very nice because the volume of such nodes, so this is the volume of one equivalence class, where I've included a Jacobian factor in analogy with how we expect Jacobian factors to appear in real ADS space, is some nice factor in a way that if we have some functions which are constant on each equivalence class, then something which we are familiar with from, say, general relativity, a measure, an integral, some action written as integral over p-Ads, actually turns into a discrete sum over the Bruhat-Tits tree. So we can actually start with more general actions which reduce to the simple actions we've been considering on the Bruhat-Tits tree. So now we can go further. We can actually form smaller equivalence classes. So we can form equivalence classes defined by this little m, which say that if 2 points are within p to the minus 2m of each other, then they are equivalent. And for different values of m, you can set m equals 1, 2, 3 up to infinity. And what happens is you get this tree structure. So the gray lines are the Bruhat-Tits tree, the original space. And the pink lines are what you get when you set m equals 1. So these are the 2 additional points inside each. So here the zoom in version might be more intuitive, that each node has 2 nodes inside, and each of these has 4 nodes inside, and then each of these has 4 nodes inside. The numbers are happening because we have chosen here p equals 2. But for general p, you can work out that there is some general nice formula, and you have a tree which goes to infinity in the up direction. And the terminus of that tree at infinity gives the full p-Adic p-Ads space. So the Bruhat-Tits tree is, a very coarse-grained version of a much larger space at infinity here, which we get from these equivalence classes. So this is a very nice place to study sub-ADS effects and like more richer theories in the bulk and on the boundary. And not a lot of work has been done on this. There was one paper on this with some partial work, but I think this is a great place to study holography or like quantum field theory, etc. Okay, so I'm running out of time. So I'm just going to spend 1 more minute here and then I will stop. So this is the second way of filling up space in the Bruhat-Tits tree. And this is not our work, so we will probably go quicker. So this goes under the class of non-Archimedean analytic spaces. So let CP be the completion of closure of QP with respect to the non-Archimedean norm. We know that like QP, CP has totally disconnected topology. But we can define some analytic spaces like, for instance, the Berkovich affine line, which is actually a path-connected topological space which contains CP as a dense subspace. And we can turn this into a projective line by 1-point compactification. And then the P1 of CP is contained as a dense subspace. So there is a way of defining Berkovich spaces. There's multiple ways of defining Berkovich spaces. One of them is as the space of all multiplicative seminorms on some polynomial ring CP of T. So the point is that the Berkovich projective line actually unifies something called a hyperbolic space and the boundary of hyperbolic space into one object called the Berkovich projective line. And this is actually interesting because the boundary of hyperbolic space contains all possible projective lines over all possible extensions of QP. And the hyperbolic space actually contains all possible Bruhat-Tits tree for all possible extensions of QP. So let me show a diagram and then end. So this is a very partial visualization of Berkovich projective line. Each point where there is branching, there is actually infinite branching. And this is an infinite tree. And it turns out that the Bruhat-Tits tree is embedded inside this space. And I've shown just one Bruhat-Tits tree, but this is p equals 3, I think. So Bruhat-Tits tree for all extensions of Q3 are stored inside the Berkovich projective line. So it's like, I think it's more similar to maybe what you might want to study for closed string theory on non-Archimedean spaces. And the nice thing is that most of the results from p-Adic holography, which people have been working on for years, naturally embed in this larger space. So the question becomes, can we actually develop a version of holography?
Can you go to the conclusion now at the
Yes.
end of the time? Okay.
Yes, I'm at the conclusion. Thanks. So I guess this is just a repeat of what I said, that non-Archimedean holography is computationally simpler, and it has real useful applications to real holography. And we can also kind of go beyond the kind of conventional holography people have studied to study small scale effects, like what I call sub-ADS effects, by adding extra points, for instance, by going to p-ADS space or Berkovich analytic spaces. And so the outlook, I guess I have some questions here. I will just write them down. So I guess some of the bigger questions are, what are the mathematical principles of holography? What are the origins of the product formulas we are seeing? And can we use these richer spaces to study a richer class of CFTs than has been possible so far? Can we extend the ADS CFT construction to refinements of Bruhat-Tits tree? And actually, can we also extend beyond real valued operators to p-Adic valued operators? And finally, I think the main question of Professor Berkovich is, can we make the p-Adic formalism fully equivalent to Archimedean formalism? We were able to use the p-Adic formalism to obtain some new Archimedean results, but it is a far cry from being on an equal footing. So at this point, I would like to thank you for your attention.
Yeah, thank you, Sarthak, for very nice, very interesting talk.